So when we want to diagonalize a matrix, we need the eigenvalues to be the entries of the diagonal matrix and the eigenvectors to be the columns of the invertible matrix. So let's see how this works, because we have to be careful. We can't just throw all these things together. Since the matrix A, 7, -4, 2, 1, has eigenvalues 3 and 5, the 3 and 5 will be the entries in the diagonal matrix. So D, our diagonal matrix, I'm going to put them down in the order 3, 0, and then 0, 5. Although we don't have to put them in this order. The invertible matrix, since I put 3 in the first column, I'm going to have to use the eigenvector corresponding to lambda equals 3 in the first column of my invertible matrix. So that'll be 1, -2. And then 0, 5 is in the second column, is the second column at the diagonal matrix. So the vector corresponding to lambda equals 5 will be the second column of my invertible matrix. 1, -1. So when I say diagonalize a matrix, you need to find a diagonal matrix D with eigenvalues on the main diagonal and an invertible matrix P whose columns are eigenvectors. We just have to make sure that we get the correspondence correctly. So lambda equals 3. There's the corresponds to 1, -2, and lambda equals 5 corresponds to 1, -1. So make sure that the first column eigenvalue corresponds to the first column in the invertible matrix. This means that we have another choice for how we can write D. We can also say that D is equal to 5, 0, 0, 3, but then we would have to construct P in the other direction. So 5 corresponds to 1, -1, and since 5 is first here, the first eigenvector will have to be 1, -1. And since 3 is in the second column, its eigenvector will have to be in the second column. Because once again, 3 corresponds, oops, I missed. 3 corresponds to 1, -2, and 5 corresponds to 1, -1. I think I was writing -1, 1 yesterday. It doesn't matter. I just need a multiple. So we have 2 choices of diagonal matrix in this case, because I can put the eigenvalues in whatever order I want, but that determines how I write the eigenvectors. We actually have an uncountable infinity of choices for the matrix P, because I just used 1, -1, but this could be any multiple of 1, -1 that I happen to find convenient. So I could use 10, -10 if I know things are going to be decimals and I want the answers to be integers. Any questions? All right. So this is so the only what needs to happen to make a matrix diagonalizable, an n by n matrix diagonalizable, is that we need to have n linearly independent eigenvectors. So the reason that we need, if a matrix is diagonalizable, it must have n linearly independent eigenvectors. Since we need an invertible matrix, oops, n by n A must have n linearly independent eigenvectors. What this means is that we are not always going to have, a matrix is not always going to be diagonalizable. Okay. So also recall yesterday we had a 3 by 3 matrix and we only had 2 distinct eigenvalues. So We also looked at the matrix, I think I called it B. And it was the matrix by columns 1, -3, 3, 3, -5, 3, and 3, -3, 1. And it only had the eigenvalues of -1 and or 1 and -2. So this matrix that I called B yesterday has eigenvalues 1 and -2. The basis corresponding to 1 was one-dimensional. So the basis for lambda equals 1 was the vector 1, -1, 1. And the basis for lambda equals -2 had two vectors, -1, 1, 0, and -1, 0, 1. So the matrix B has 3 linearly independent eigenvectors. So the matrix B is diagonalizable. B has 3 linearly independent eigenvectors. So B is diagonalizable. Since B has 3 linearly independent eigenvectors, B is diagonalizable. That means we can construct a diagonal matrix D and an invertible matrix P such that B is equal to B is equal to P, D, P inverse. So in this case, we only have 2 eigenvalues, and the diagonal matrix D has to be 3 by 3. Otherwise, our multiplications ain't going to work out. But the lambda equals -2 has been repeated. So our diagonal matrix D, which has to be 3 by 3, I could put 1 in once, and we're just going to put -2 in twice. Since the lambda equals -2 has multiplicity 2, it corresponded to a 2-dimensional eigenspace. I'm going to put it in twice in my diagonal matrix. And then when I construct the invertible matrix P, I will make sure that things correspond. So I'll write, since I wrote 1 first, that eigenvector has to go in first. Then the second column will be the 2 vectors in the basis corresponding to lambda equals -2. So I'll put in -1, 1, 0, and -1, 0, 1. And that's it. So since lambda equals 2 corresponds to a 2-dimensional eigenspace, I put in lambda equals -2 in the diagonal matrix twice. Because the lambda equals -2 appears twice in the diagonal matrix. Since lambda equals 2 corresponds to a 2-dimensional eigenspace. Once again, I have 3 different choices for how I could write D. I could write it as 1, -2, -2, or I could write it as -2, 1, -2, or I could write -2, -2, 1. If I start rearranging the vectors in D, sorry, the entries in D, I would have to start rearranging the columns of P. We just got to make sure that things line up correctly. So this 1, 0, 0 has to correspond to its correct eigenvector. Any questions? So those are the matrices that we looked at yesterday. And if I say diagonalize a matrix, and all I do is give you a matrix, then you have to first find the eigenvalues using the characteristic polynomial, then find a basis for the eigenspace corresponding to each eigenvalue, and then you can construct the matrix D and invertible matrix P if you have a sufficient number of linearly independent eigenvectors. Let's do an example where things don't work. Let's make a matrix Q. Mostly because for some reason I don't like matrices named C. I don't know why. Okay, I'm going to give you a matrix. We're going to go with 2, -4, 3, 4, -6, 3, 3, -3, 1. Has eigenvalues lambda equals 1 and lambda equals -2. So like I was saying yesterday, if I give you a 3 by 3 matrix and ask eigen questions about it, I will tell you what the eigenvalues are. So I've told you what the eigenvalues are. We need to find a basis for the eigenspace corresponding to each eigenvalue. So we're going to find a basis for the eigenspace corresponding to each eigenvalue. So I'm going to start with lambda equals 1. So I'm going to subtract 1 from the main diagonal. So we're going to solve, so IP. Remember, to find this eigenspace, we solve Q minus lambda I times X equals 0. So we solve a homogeneous equation. We know that there's non-zero solutions because lambdas are eigenvalues. So we need to be able to find a non-zero solution to the homogeneous equation. Because that would mean, because if all we get is a 0, that means our lambda is wrong because this Q minus lambda I is invertible. So I'm going to write Q minus lambda I. So I'm going to 2 minus 1 is 1, -4, 3. And then -6 minus 1 is -7, 3. And then 3, -3, 1 minus 1 is 0. So because it's so early and I haven't finished all my coffee, I'm gonna just not hide the matrix. So I got 1, 4, 3, -4, -7, -3, 3, 3, 0. I don't need the last column because I'm solving a homogeneous equation. I know the last column is all zeros and it will stay all zeros. So I get this. I get a one-dimensional eigenspace. So the reduced echelon form is going to be 1, 0, 0, 0, 1, 0, -1, 1, 0. So this gives me an x1 is x3, x2 is -1 times x3, and x3 is free. I get a one-dimensional eigenspace. So lambda equals 1 corresponds to the eigenspace 1, -1, 1. If Q is diagonalizable, then I'm going to need 3 linearly independent eigenvectors. And you can probably guess, based on the law of mathematical opposite examples, what's going to happen with lambda equals 2. So let's find out. So now we're going to look at we're going to find a basis for the eigenspace corresponding to lambda equals -2. I'm going to write the reduced echelon form. So I got 2 minus a -2 is going to be 4. So 4, -4, 3. Then I got 4. -6 minus a -2 is -6 plus 2, so that's -4. And then 3. And then the last column will be 3, -3, and then 1 minus a -2 will be 3. Find the reduced echelon form. Once again, this one did not come out to one where I can just read it because it's too early. But I got 4, 4, 3, -4, -4, -3. At least that one's easy to see. And then 3, 3, 3. So we see we get 1, 1, 0. So we get a free variable, and we get only one free variable. Sentence started to come out weird. So remember, this is the coefficient matrix. So we've got 2 pivots still. Pivot here and pivot here. So this tells us that x1 is equal to minus x2. x2 is the free variable, and x3 is equal to 0. So our basis for the eigenspace here is going to be -1, 1, 0. But we only got a one-dimensional eigenspace. Should be 3. Last row is 3, 3, 3. So I've got the last row is 3, 3, 3. That's what we want. So 4, 4, 3, -4, -4, -3, 3, 3, 3. Yeah, that's what we want. Type it in by rows. So we found a basis. We found a basis. Basis corresponding to lambda equals 1. I kind of hate this notation, but it'll do. And here's our basis for lambda equals -2. That we can always do. Once we have the eigenvalues, we can always use the eigenvalues to find a basis for the corresponding eigenspace. Now we can see in this case that the matrix Q is not diagonalizable because Q only has 2 linearly independent eigenvectors. So we see that Q is not diagonalizable. Oops, spelled E wrong. So on a quiz, a test, or a final exam, I want you to ask you to diagonalize Q or explain why Q is not diagonalizable. That's how I would phrase the question, whether it's diagonalizable or not, because I always have to leave open the possibility that none of the above is an answer. All right, so in this case, Q is not diagonalizable because there are only 2 linearly independent eigenvectors. And Q is 3 by 3. Q is not diagonalizable since there are only two linearly independent eigenvectors, and Q is 3 by 3. The important part of this sentence is the linearly independent eigenvectors. We only wrote down two eigenvectors, but there are way more than two eigenvectors. There are uncountable infinity of eigenvectors, but there are only two linearly independent eigenvectors. Because remember, if I multiply -1, 1, 0 by Q, I'll get just -2 times -1, 1, 0. But if I multiply 5, -5, 0, I would just end up with -10, 10, 0. So there are only two linearly independent, Q only has two linearly independent eigenvectors, and Q is 3 by 3, so Q is not diagonalizable. We cannot construct an invertible matrix P. There's no way to build the invertible matrix P. I've only got two linearly independent eigenvectors. If I just use a combination of those, then my matrix is not invertible. Any questions? So these three examples represent the most that I would ask you to do on a quiz, a test, or a final exam at this point in the semester. If I gave you a 2 by 2 matrix, I could just say diagonalize a matrix, in which case you have to use the characteristic polynomial to find the eigenvalues, then use those eigenvalues to find the eigenvectors, then construct your diagonal matrix and your invertible matrix to diagonalize the matrix. Or if I give you a 3 by 3 matrix, I will tell you what the eigenvalues are, even though I know y'all can find the eigenvalues. I would tell you what they are to save you the trouble of solving a cubic equation. Mostly because what will happen is you'll come across the cubic equation, and then you'll use a machine to solve it, at which point I'm like, oh, dude, if we're just going to use a machine to find the eigenvalues. Heck, use a machine to diagonalize the matrix. Any questions? All right, let's stop the video here on diagonalizing matrices and talk about what our next steps are.